Welcome to our presentation today. We're going to be talking about GeoEvent Server and developing custom components using the GeoEvent SDK. My name is Eric Ironside, and I'm a product engineer on the GeoEvent team.
And I'm Brett Phillips, a software engineer on the GeoEvent team.
So before we get started on talking about the SDK and customizing GeoEvent, let's talk a little bit about what GeoEvent is. GeoEvent Server is a functional role bringing real-time GIS to the ArcGIS Enterprise. It provides 5 key capabilities when working with your real-time data. The first is ingesting high volume and high velocity data from connected devices, sensors, and the larger Internet of Things landscape. The second is to refine and enrich that data and to identify patterns of interest on the fly using real-time analytics. The third is to introduce a big data storage solution to support the volume of data being received, one that can be scaled and can support the configurable retention settings that are required for real-time data. The fourth is to extend the visualization capabilities of the ArcGIS Enterprise through stream layers for live feeds, as well as both dynamic aggregations and discrete feature displays through enhanced map services. And finally, the fifth is to be able to disseminate information and actuate back into the devices in the field and directly impact the environment in which those devices reside. So this is our agenda for the session today. The first thing we're going to talk about is creating and configuring connectors in GeoEvent Manager without custom development. Next, we will review the GeoEvent SDK at a high level, going through all of the things that it provides for customizing GeoEvent. Then we are going to walk through developing each of the custom components that are available through the SDK. And finally, we will wrap it up with some odds and ends and a review. Okay, so the first thing we're going to talk about is configuring connectors, which can be done without any custom coding. Functionally, when a user selects an input or an output, he implicitly selects the component inside the GeoEvent server that knows how to receive and send data. We call that component the transport. And the component that knows what the data looks like, which we call the adapter. The adapter can convert raw data to and from GeoEvents. The connector is a unique combination of one transport and one adapter. So let me walk you through an example of how this works for inputs and outputs. First, the input is created based on a connector, and the connector was defined using a TCP transport and a text adapter. Once the transport is started, it accepts the raw bytes over TCP. This stream of bytes is passed to the adapter for parsing. The adapter parses the bytes and produces GeoEvents that are sent out to all of the different services. On the output side, we've defined the connector as a JSON adapter and an HTTP transport. So the output, the reverse happens from the input. So the adapter accepts the outgoing events from the services. It deconstructs the GeoEvent into the outgoing format, and then the transport takes that data and sends it along. And all of this happily occurs until the transports are stopped. As I said, a connector functionally provides the user the ability to create inputs and outputs. A connector's purpose is to hide the technical details that the end users don't really have to care about. Some properties may be hard-coded and hidden entirely. Others may be moved under the advanced section and get default values that users may only rarely change. Finally, a connector can be used to provide contextually specific property labels, so it's clear to the user exactly what's expected. A connector can be very specific. For example, logging into a dedicated REST data feed where a token may be reused for every input created, or it can be more general and generic like this RSS data feed connector here. I have mentioned that inputs are defined by input connectors. An input connector is a combination of an inbound transport and an inbound adapter. This slide illustrates how an input connector is created using available transports and adapters. For example, the received GeoJSON on REST is composed of an HTTP inbound transport and a GeoJSON inbound adapter. Similarly, a receive feature JSON from Kafka connector can be created from a Kafka inbound transport and a feature JSON inbound adapter. It's important to note that you can create a new connector that isn't part of the core offering by combining existing transports and adapters. You can do all of that on the GeoEvent Manager without writing any custom code. The slide also shows the inbound transports and inbound adapters that are available out of the box, as well as some of those from the Esri gallery that are available to be added to your GeoEvent. Similar to inputs, outputs are defined by output connectors. An output connector is made up of an outbound adapter and an outbound transport. For example, the send an email output connector is composed of a message formatter adapter and an SMT transport. A publish feature JSON to Kafka connector would be composed of a feature JSON outbound adapter and a Kafka outbound transport. There's a variety of outbound adapters and transports that are available out of the box, and more can be found on our gallery. So far I've mentioned the GeoEvent Server gallery for finding custom components. This gallery offers a set of adapters, transports, and processors that are not part of the box installation, but they can be added to your GeoEvent if you need them. Deploying a component is pretty easy. First, you have to get a hold of the jar file. Usually this is contained in a zip file that you download from the gallery. Next, you have to upload that jar file into GeoEvent Server. You can do this in one of two ways. The first is you can copy the jar file directly into GeoEvent's deploy directory, which is found under GeoEvent's installation directory. This is probably the preferred method of doing things. The second option is you can upload the file using GeoEvent Manager's Add Local buttons. These can be found on the Site tab under the Components menu. There is an issue there sometimes where the jar files won't upload through the GeoEvent Manager user interface. So if that happens, just copy it into the deploy directory. Please also note that in order to remove a custom component from GeoEvent, you must delete it from the deploy directory. There is no GeoEvent Manager method for removing custom components. And with that, let's go ahead and take a look at a demo of how we can create a custom connector and import custom components. Okay, so here we are in GeoEvent Manager. We are on the Site tab at the top and the connector menu item on the left-hand side. This gives us a list of all of the connectors currently configured in GeoEvent. We can filter by inbound or outbound connectors, and we can search for connectors. So looking for watch shows me all of the inbound connectors that watch folders. You can see we have 3 connectors, but there isn't one for XML. So I can click on the Create Connector button to create a new one. Here we're going to fill out a name, watch XML, add a label, watch a folder for XML, set a nice descriptive description, and this is an input connector, so we're going to select input, and we'll select the XML adapter to parse our incoming data, and we'll choose the file transport to watch a folder for new files. And finally, we're going to give it a default name so that when you create a connector or an input, it will have that name. Now we're ready to set up the properties. So scrolling down, we see that we have a variety of properties to configure down here. XML is a text file, so we'll hard code that to be true and save that. And since the user is never going to need to set that again, we can move it into the hidden properties section. And we can do that for the batch flush interval, because that's not going to be something that the user is going to want to be setting. And we'll move that to hidden section as well. And then for all of the other properties related to the geometry, we can just move those into the advanced section, because I don't expect that the users will have to work on those every time. And then we'll hard code the channel ID and hide that property as well. Okay, so now I'm going to modify the order of the shown properties. So we'll move that one up and move this one down here. And finally move that one up. Okay, now that we've got all these set up, we could come in and modify the labels for each property if we needed to, but in this case, I'm not going to. So now we're going to go back to the top and save this connector. And now you can see if I type watch again here, we find our new inbound connector. So now I'm going to go back to the service tab at the top, and we're going to go into the inputs, and we're going to add a new input. And we're going to type watch to search. And if I scroll on down here, we see our watch a folder added XML input. You can see we've got all of the items that we set up to be shown previously at the top. And for the advanced sections, expand this down here, we can see down here that we have all of the advanced properties like the geometry properties here. Also notice that none of the hidden fields are available. So I could use this dialog to create a new watch folder for XML files input. I'm going to cancel for now. So that's how you can configure. But when it comes to deploying new items, like let's say you want to go over to the GeoEvent gallery and you want to define the field splitter processor. We can read through the description here and decide that's what we want. So we'll scroll down and we'll grab the latest release, release number 7 here. And that's going to download that zip file for us. And if we open up that zip file, we'll see the documentation, release notes, and all that sort of stuff. What we're really interested in is the components folder. There's a couple jar files in here. So I'm going to grab the jar file and throw it onto my desktop. Back in GeoEvent Manager, I'm going to go back to the Site tab at the top right here. And the components item on the top, and click on the, under components we see transports, adapters, and processors that are currently available in GeoEvent. We're going to go to the processor tab here, so I'm going to go and search for field splitter. And it isn't in there already, so I will need to add a local processor. And we're going to go find that jar file that we put in our documents folder. Open that and click add. All right, it says it was imported successfully. And if we do our search one more time, we see that we have the multi-cardinal field splitter in the list. The version here is listed at 10.4.0. Things are always forward compatible, so that should be fine. And then we have release 7 as well, which is what we downloaded. Now going back to services, add a new GeoEvent service. Just call this test 1 since I already have a test in there. And if I grab a new processor and grab that, put that onto our service designer, you can see in the list of processors we do have a multi-cardinal field splitter now. So we can add that to our service. One thing to note here, if you look in the file system under GeoEvent Server installation folder, in the deploy directory, the deploy folder contains all of the jars that have been deployed to GeoEvent. So you can see here's our multi-cardinal jar that we just updated. If you wanted to bring in the other field splitter jar, I could just copy it directly into the deploy folder. I don't have to go through GeoEvent Manager. Once I've done that, I can go back here and add a new processor. And if I drop the list of processors down, we can see that field splitter is now available. So simply adding the jar to the deploy file made that available. Another thing to note about the deploy directory is that deleting a jar file removes it from GeoEvent as well. So we're going to delete that field splitter that we just threw in there. And go back in GeoEvent Manager looking for the field splitter processor. And we drop the list down and it's no longer in the list there. So you can see that it updates immediately. Okay, but what happens when the out-of-the-box options aren't enough and there just aren't any components on the gallery that fit your needs? This is where the SDK can come into play. So this slide summarizes where you can add your own code to GeoEvent Server. You can customize inbound and outbound connectors, and you can customize processors. So the GeoEvent Server does come with an SDK, which allows you to build all of these custom components. The GeoEvent SDK provides a number of resources to accomplish these tasks. The GeoEvent SDK is installed along with GeoEvent Server, and it can be found in the GeoEvent Server's installation directory. You can see here a snapshot of the SDK folders that are installed. So first there's an API folder, which has the Java doc that describes the API. If you open up this folder and open up the index file that's on there, you will be able to see and browse all of the documentation related to all of the SDK interfaces that are exposed. It also has a repository folder that contains a set of libraries that you can use to compile against when you're developing your custom code. And then there's the samples folder, which contains 12 sample projects for adapters, transports, and processors. These are updated for each release, reflecting any changes that are made in the SDK, if there are any. Generally speaking, the SDK is forward compatible. I found for most projects, I can compile against the 10.4.0 version of the SDK and still be completely compatible with any of the later versions. And then finally, the developer guide describes the software architecture, how to work with GeoEvents and GeoEvent definitions, and how to use the Eclipse IDE to write and debug some of the components. It also describes in detail what the takeaways are for each sample. So before you start working on anything custom for GeoEvent, you should definitely read the developer guide and review the sample projects just to make sure that you understand the basic ideas for developing custom components. Here's a look at what it takes to create a transport adapter or processor. Programmatically, each component has 4 basic pieces. So first, there's the configuration. This provides the instruction to the underlying OSGI framework for how to create your component. Next is the service. The service is a factory class to create new instances of your component. The definition is the class that defines the metadata and properties of the component. And then finally, there's the implementation itself that contains the application logic, such as reading files from a folder. You'll see the same implementation pattern repeated for transports, adapters, and processors. So all of them in your projects, you'll have the configuration, the service, the definition, and the implementation. Diving a little bit deeper into each one of these classes, the configuration is based on Blueprint, which is a Spring-like configuration that tells GeoEvent Framework how to instantiate and configure your service class. So the bean part tells the framework which Java class to load and what dependencies it has. Some of these dependencies are required, like the bundle context that you see here, and some are optional depending on what you're doing. So the data folder and also the messaging here. So the messaging is a reference. So references are used to call out specific GeoEvent SDK items that your implementation may need, such as the messaging service to create new GeoEvents. And then finally, the service tag at the bottom here exposes the bean wrapped in the appropriate SDK interface. So in this case, it's an adapter, so we're wrapping it in the adapter service. The service class is responsible for loading the definition and working as a factory for creating new implementation items. So in this case, it's responsible for creating a new adapter. So the part in green here is the part that's required for all service implementations or service classes. Note that the optional data folder that we had in the previous configuration is at the bottom here. This is just an optional thing that's been added. It's not required for base service classes. So it depends on what you're doing and what additional SDK resources you might need. The definition class provides metadata to identify and describe your component. You can use localized strings for each of these components if desired, but it's not required. Another note here on the localization and using strings, do not use the com.esri.ges to start your domain because that's a reserved keyword or reserved path for out-of-the-box components. So if you do that, GeoEvent may confuse your custom item for an out-of-the-box item and do strange things with it. So I always use com.esri.geoevent as my start of my package, but you might insert your company name rather than Esri in there. Continuing on with this example from the previous slide, we next have to define the properties of the item we're creating. So for each property, we can define things like the name, the type, the default value. We can restrict the user's response to a list of defined labeled values. So in this case, we're doing compression algorithms. So we give them a specific list of algorithms we're expecting. We can use localized strings for the label and the description here. So using the same notation as we saw in the previous slide. And then finally, we can make properties dependent on other property values. So for this case, if the user wants to compress the data, then they should see a compression algorithm. But if they don't want to compress the data, then the compression algorithm should not be shown. Once a property is defined, we have to add it to the properties definitions list. So that's how you would create properties, and you would repeat this multiple times for the different properties that you have in your definition. There's a few other functions that can be achieved through the properties. So one of the things that a property can do is to set itself to be mandatory, as the name is here. You see the red asterisk there indicating that the user must enter that data. or optional, such as the URL here. So the user does not have to create or enter a URL into this text box in order to save this input. Properties can be dependent upon other properties as well. So for example, from the previous one we saw the compression algorithm, if the user does not want to compress the output, then there's no reason to show the compression algorithms. But if we change that to yes, then we definitely want to show the compression algorithm and give them the option to choose. So the predefined values will then show up in that list as we saw in the previous definition. Also, as I mentioned earlier, component definitions can be created either through a Java class or XML. This slide just shows an example of an XML-based component definition. So it starts at the top with the attributes for the component. This includes the name, the label, the contact, and the description. The label and description can be localized once again using your localization strings here. And then there's a list of properties that the user can set to define the component behavior. The property definitions have their own attributes such as name, label, description, property type, default value, and so on. It's very similar to what you saw in the Java example above. Finally, note that on the syntax of using localized strings, so this is kind of applies throughout GeoEvent when you're working either with your definition or in your other areas of implementation. GeoEvent uses a $, curly braces notation to indicate that you want to localize a string. So anytime it sees that, it's going to go try to replace that with the string from the strings files. Which property file it uses depends on the locale settings of the user's browsers and whether or not there's a file available for that localization. And with that, I'm going to turn it over to Brett to dive deeper into developing each of these components.
Thanks, Eric. So we've learned about connectors and the different parts involved in creating custom components at a high level. Now we are going to dive deeper into the implementation classes of these components. First, we are specifically going to talk about how we can develop our own custom transports in order to handle the flow of our data. Before looking at the code, it's important that we first analyze a transport's lifecycle. This will give us a better understanding of how the code works. A transport has 5 stages in its lifecycle, and it first begins in a stop state. It will stay here until the user chooses to start the connector from within the UI. Upon starting the connector, the server will call the start method, sending the transport into the starting state. This is where the transport will read as well as initialize its properties and officially start. It will then stay in this started state until the user decides to stop the connector through the UI. This causes the server to call the stop method, sending the transport into the stopping state. Now in the stopping state, the transport will close its resources, and once this has been completed, the transport will officially stop. Throughout the lifecycle of a transport, there could be many errors that occur. If there are any errors, then we enter in an error state. And in this state, we can log the message of the error using the bundle logger. We will talk about the bundle logger a little later in the presentation. Now we are going to look at the lifecycle in more detail from a code standpoint. First, we have the creation stage. It is important to extend the base class, in this case the inbound transport base, since we are working with an inbound transport. This gives you functionality out of the box that you normally would have to write yourself but is already provided. The transport service will instantiate this implementation class, passing it a reference to the transport definition. This definition is then used as a parameter for the base class constructor. Once the transport has been created, the afterPropertySet method gets called, and this is where you will initialize the transport state. The getProperty method from the API will help you retrieve any user-defined properties that are needed in order to initialize the state of the component. In this example, we are retrieving the event size property, casting it to an integer, and assigning it to the event size instance variable. After the transport has been initialized, you can now validate its properties to ensure their accuracy via the validate method. The super.validate method call will check against the types of those properties, as well as if any of those properties were required but left empty. You can also add in your own functionality and checks to this method if needed. At this point, the transport has been successfully created, initialized, and validated. Now we can go ahead and handle the event-driven methods. When the user chooses to start the connector from within the UI, the start method gets called. This is where you will go ahead and tell GeoEvent that it can begin consuming events. Here, we set the running state to starting, instantiate a new thread, and start that thread. As a result, this will kick off the run method, beginning the flow of data. The top picture here shows the receive implementation for an inbound transport. Inbound transports are responsible for sending data from connected devices to inbound adapters, and specifically the inbound adapter's byte listener. In this example, we are constructing a buffer with the data and passing that buffer to the inbound adapter through its byte listener. The bottom picture shows the receive method for an outbound transport. Outbound transports are responsible for receiving data from the outbound adapter and disseminating that data back to the connected devices. This process is all handled within the receive method. Lastly, when the user chooses to stop the connector through the UI, the stop method gets called. The super.stop method call will set the running state to stopping, thus preventing the further consumption of data. So now that we know how to move data in and out of GeoEvent Server, we need to be able to adapt our data into something that GeoEvent Server can read and understand. We refer to this as a GeoEvent object. Unlike transports, the adapter is unique in the sense that it does not have its own lifecycle. Instead, it is a completely event-driven component. However, similar to transports, we still need to extend from the base class. In addition, the adapter service will create an instance of this class, passing it a reference to the adapter definition. This definition is then used to call the base class constructor. We then go into the AfterPropertySet method, which we can override in order to retrieve any of those user-defined properties via the getProperty method from the API. During this process, a GeoEvent listener is also set, which tells the adapter where it can send any GeoEvent objects that it creates. When an inbound adapter receives raw data, it is in charge of converting that data into a GeoEvent object. This is the base class for the inbound adapter that you will need to extend from. It is important to note that it is in fact an abstract class, meaning you will have to implement all of its abstract methods. In this case, there is only one. You will implement the adapt method to handle the data conversion from raw bytes into a GeoEvent object. The adapter's receive method is then passed a reference of the new raw byte data from the inbound transport that needs to be converted. The implemented adapt method is called in here, again handling that conversion. It then takes the constructed GeoEvent object and calls the GeoEvent listener's receive method in order to pass the newly created GeoEvent object to the outbound adapter. You can also decide to override the receive method if you need to handle your own additional business logic. If you do this, then you will need to manually call the GeoEvent listener's receive method, as well as implement the adapt method by returning null. For the outbound adapter, you will need to override the receive method. This will allow you to convert any GeoEvent objects that are incoming from the inbound adapter. Once you have converted the data from a GeoEvent object back into bytes, you can pass it through the byte listener's receive method, sending it to the outbound transport. Up to this point, we have learned how we can move and adapt our data into GeoEvent objects. Now we can perform analytics on those objects through the use of processors. Similar to a transport, a processor has 5 stages in its lifecycle. First, the user will publish or start their GeoEvent service. This will cause GeoEvent to begin looking for the processor service, and once found, will create an instance of that processor, passing in a definition and any user-defined properties. These user-defined properties are then used in order to initialize the processor's state. Once the state of our processor has been initialized, we can validate it, where we can check those user-defined properties for their accuracy. At this point, the processor has been successfully created, initialized, and validated, and we are ready to start consuming GeoEvent objects and performing analytics on those objects. That takes us to the processing stage. The processor will remain within this stage until the user decides to stop the GeoEvent service. This will cause the processor to shut down, freeing up any unneeded resources. Just like the other components, you will extend from the base class in order to acquire that needed functionality. The processor service will instantiate this class, passing in a reference to the GeoEvent processor definition, which is used to call the base class constructor. We then go to the afterPropertySet method, which is used to initialize the processor's state with any user-defined values. The getProperty method will allow us to retrieve those values, and in this case we are retrieving the GeoEvent definition name and add center point properties as strings and assigning them to local variables. We then have the ability to use the validator and converter classes, which are static helper classes that help us further handle those retrieved properties. Here, we're using those static classes that I mentioned to compact the white space in the GeoEvent definition name and convert the add center point property to a Boolean. Once the state of our processor has been initialized, the validate method gets called. Here, we can go ahead and check the processor's state with those user-defined properties. The super.validate method call, like I talked about earlier, will check the types of those properties and ensure those required properties are not empty. Here, we also do some additional logic to check the value of the GeoEvent definition to ensure that it is not empty. If it is, then we use the bundle logger to log an error. After validation, we are able to begin processing events and performing analytics. In this case, we are augmenting the incoming GeoEvent object by getting its GeoEvent definition and updating it, adding on an extent property. So we are adding on an xmin, xmax, ymin, ymax. Once this has been completed, we return the modified or mutated GeoEvent object so that it can be passed between the other nodes within the service. Lastly, we have the shutdown stage. These are all optional methods, but helpful if you want to do some resource management. The shutdown method is called when GeoEvent Server is shutting down, and will clear all the properties. Note that I did say GeoEvent Server and not the GeoEvent Service. The onServiceStart method is called when the user is publishing or starting a service. So here's where you will want to perform any initial logic that may be needed for your processor. On the contrary, you've got the onServiceStop method, which gets called when the user is stopping a service. So any cleanup of a processor's resources can be cleaned here. And is GeoEvent Mutator. For performance reasons, we do not copy GeoEvent objects between nodes. Instead, we pass them as read-only. Therefore, if you will be mutating GeoEvent objects, then you will want to override this method and return true. Now with that, we're going to go into a demo where we will import, deploy, and validate an existing processor. I have downloaded a project from one of the GitHub repositories, so I'm going to go ahead and import that project. When I import that project, IntelliJ will then ask me how I want to import it. I'm going to make sure that Maven is selected. My root directory is fine. I do not have any profiles to select. And then it'll ask me to select a Maven project to import. In this case, I'm only going to import one. Make sure it is selected and click Next. I will then choose my JDK, the project name as well as the project location, and hit finish. Once IntelliJ finishes indexing my project, we can go ahead and start. Inside our project, you'll notice that we have a POM file, and inside this POM file, we have a group ID as well as artifact ID. We also have dependencies that are needed in order for our project to build successfully and run. Here we have our GeoEvent SDK. If we go inside the source folder, you'll notice we have two folders, a Java folder and a resources folder. Inside the resources folder is our blueprint configuration, which follows the OSGI package structure. And then inside our Java folder, we have our processor definition, and processor service Java classes. First, we're going to take a look at the processor definition. Inside the processor definition, we have a delay value and delay value units. We also specify the property type as well as its default value, labels, descriptions, and other properties. We could utilize these labels and descriptions as localized strings, but in this case, we're just going to use English. Inside our processor service, we are instantiating the processor definition. And then when we create our processor, we are passing it a reference to that definition. Inside our processor, our constructor brings in that definition and uses it to call the base class constructor. Once this occurs, we can now set and initialize our processor. This is when we use the afterProperty set method. Here we're using the API to get the value for delay value as well as delay value units that the user has defined. Our processor will start once the GeoEvent service gets published or started. That will start this method, which will handle our event loop. Once this has been completed, we are then ready to start processing our events. Our process method will take in a GeoEvent object, take one of the user-defined properties, delay value, convert it to milliseconds based on the unit that the user provided, and then we'll create a delayed GeoEvent object, passing in the GeoEvent and how long to delay the processing. It will then put it into a GeoEvent queue, and once we're in this queue, we will wait until the specified time has gone by before we send that GeoEvent object. When the user stops the service, the onServiceStop method gets called, and this is where we will clear our GeoEvent queue. The other important thing to mention is that we also are utilizing and overriding the shutdown method. So when GeoEvent Server shuts down, we are shutting down our executor service. Now we are ready to build our project and import it into GeoEvent. We're going to go inside the terminal. Notice how we are in our project, and we're going to type in Maven clean install. This will kick off the build process and will build our project. Once this has been completed, you'll notice that we now have a target folder. And inside this target folder, we have a jar file. This jar file can be used in order to deploy our processor into GeoEvent. I will now hand it off to Eric, who will show you how to deploy that and actually validate your processor to ensure that it is working correctly.
Thanks, Brett. Okay, so I've gone ahead and grabbed the jar file that Brett created there, and I've thrown it on my desktop here, so I've got it sitting right here. It's not too big, so I'm going to go ahead and use the GeoEvent Manager to import this. Just note there is a kind of an issue on the GeoEvent Manager that allows you to import jar files that are 100 kilobytes or less. We're working on getting that fixed, but for right now, that's a limitation. And I'll show you how to get around that in a little bit here. So I'm in GeoEvent Manager here, and I'm on the Site tab in the Components menu under Processors. And this gives us a list of all of our processors that we have here in this GeoEvent server instance itself. These are all out-of-the-box components. So I'm going to add this new jar file that Brett sent to me. And we're going to go to the desktop. And grab the jar file. And open that up. And we're going to hit the Add button here. And that's going to import the jar file and add that processor to our system. So what I should do immediately be able to do is to come down here and look at where this is coming from. So we have the delay processor, it's release 10, delays processing events by a specified amount. Okay, great. So now that I've got that in there, I can go ahead and use this in a service. So head back over to the services here. I've already got some stuff set up here that I was testing with earlier, and I've decided that in the processing of these events, I really need to introduce a delay. So maybe we're publishing, the locations of all of the snowplows in a city or something like that, and we want them to be, close enough, but not exactly real time, so somebody can't go out and throw snowballs at the windshields or something like that. So I want to introduce a delay in this. So I'm going to get rid of this connector here, and we're going to drag in a processor. And when I drop the list down here, we should see the delay processor, and there it is right there. So we're going to grab that. We're going to call this delay. Now the delay time, real world snowplows or something like that, you probably want to delay them by a couple minutes. In this case, just for testing purposes, I'm going to delay this by 5 seconds. So this should grab a hold of all of our events, hold on to them for exactly 5 seconds, and then release them. And so if we come in here and we hook that back up, one other thing to note is that I'm pulling data every 15 seconds. So you can see here frequency in seconds is 15. So if I publish that, and we get one in, 1, 2, 3, 4, 5, we should get one out right about now. Okay, so you can see that the counts here are staggered off since the last time. But even better, if I wanted to take a look and see exactly what's going on, I can actually use the sampler now to take a look at this. So the sampler is going to be looking at that stream, and we can see, okay, there's my data. I've got this unit's information came in, and so I've got all of that. If I actually want to see what the processor's doing to this, I can do a compare route, and that gave me that one there and there. Okay, so real quickly, I'm going to reset this. So the next one that comes in should come over here. 1, 2, 3, 4, 5, and there it is. Okay, so that's confirming for me that the delay processor is actually working, and that the event that's getting through is indeed the exact same event that we started with. So if you had a different processor, obviously you would be looking for different things between the two of them, but that shows you an example of how you could import that jar file and then validate that it's actually working using the sampler here. One other thing I did tell you that I would show you how to import the jar file without using the GeoEvent Manager user interface. What you can do, you'll notice once you import that jar file, when you do it through the user interface, is it actually just copies the jar file into the deploy folder. And this is, I use the default installation location on a Windows machine. So this is down in the GeoEvent Server installation. There's a folder called deploy. You can, in fact, just copy jar files into that directory. And also, if I delete that here and continue, that is going to, in fact, break my my service here because now I don't have that delay processor. And And if I open this up, you can see I don't have a delay processor, and I don't have a delay processor in the list here. So cancel on that, and we'll go back out here and grab this jar file. What I could have done instead of using the GeoEvent Manager UI is just simply copied and pasted that into the deploy folder. And once you do that, then everything should be running and fine. So you can see that the service started right back up. And when this gets to 5, we should see the output. There it goes. Okay, so that shows you how to deploy the jar file that you've created, and gives you an idea of how to use the sampler. And with that, I'm going to turn it back over to you, Brett, so you can take us down the home stretch.
Now that we can fully develop our own custom components, there are a few development-related items that we would like to briefly go over that will help with your development process. The GeoEvent SDK is a Maven-based project, so before beginning development, it would help to have a basic understanding of Maven and how it works. This also means that when you are creating or importing projects in your IDE, that they must be Maven projects. If not, then they will not work. For processors, there is generally one POM file for the project, but connectors generally have a parent-child set of POM files. One for the parent, one for the adapter, and one for the transport. The POM file is vital for a Maven project as it is a configuration file that contains information required to build the project. Inside the project, you will not only have the POM file, but also a Java source folder containing your Java code, as well as a resource folder containing your blueprint configuration, localization strings, and definition properties if you decide to write them in the XML format. The package structure for the localization file must match your bundle group ID plus artifact ID, and your configuration must match the OSGI structure. When creating components, it is important to have meaningful log messages that provide details about any issues that occur. In order to log messages, you will use the bundle logger factory to retrieve the logger for the class. To log a message, simply call the method for the desired log level. In this case, I'm using the trace log level, and pass in any parameters. You can pass in as many parameters as needed and use index notation to have those values inserted into the message at the appropriate location. Each log method is also overloaded, allowing you to pass in an exception. This will append the stack trace of that exception to the end of the log message. Finally, the log message itself can be localized. Throughout the development process, you may need to spend time debugging your code. To configure debugging, you must first modify the GeoEvent configuration file, which is located in the etc folder. Uncomment the identified lines and add in the correct number. These numbers will increment based on the prior property. So in this case, the prior property was 14, so I added 15 and 16. Finally, it is important to note the port that the debugger will be listening on, as this will be needed later in the process. Within your IDE, you will need to configure debugging for a remote Java application and enter in the IP address of where GeoEvent Server is running, as well as the port from the configuration file prior. In this presentation, we have thoroughly examined all the areas needed in order to successfully create connectors and processors using the GeoEvent SDK. We learned that connectors are made up of a transport and an adapter. The transport being responsible for moving our data in and out of GeoEvent, while the adapter is responsible for converting raw data to and from GeoEvent objects. These components also contain properties that enable the user to configure the transport and adapter for specific use cases. We also learned how we can apply real-time spatial analysis through the use of processors and how we can deploy those processors and use them within our UI. This slide provides a list of resources that may be helpful in finding and or developing custom GeoEvent components. The GeoEvent SDK provides a variety of simple samples that will help you get started, whereas the Esri GitHub repository is a good place to find your more advanced examples of custom components. We also encourage you to view our other technical workshops. These will help you get more familiar with GeoEvent Server, as well as provide you with further information in regard to the development of future releases. That brings us to the end of our presentation. If you do have any questions or comments related to GeoEvent, or maybe this presentation, please submit them via the following link. Thanks.